All right, recording's rolling. Welcome to Tuesday, September 26th. Got a starter question for you guys involving this Atwood. So it's the same couple questions that you normally get, right? Acceleration and tension. We're gonna knock out some textbook puzzles today. Oh, you guys remember those are due on Friday, right? Okay, meant to put that here. Due Friday. That's at 9:29. That's gonna be. I just gave you guys your forces quiz. It looks about like this. Right, got some free body diagrams. Oh, look, it's an Atwood with a couple of questions. Right? Acceleration and tension. Right? Got some other type questions on it related to stuff we've been doing in class. Right? Let's have that due on Monday, October 2nd. So you guys got a few days to do that. Right? Speaking of quizzes, projectile quiz. I'm still waiting on like 5 or 6 quizzes collectively from all my honors students. Oh, yep. Projectile quiz. Let me see if here. Yeah. All right. So yeah, I know a bunch of you guys are waiting for me to hand this back. I've had this for quite a while because this was like a couple weeks back. I don't want to hand them back until I get them all, but again, a bunch of you guys are waiting for them and wanting to do corrections to stuff like before the first 9 weeks runs out. So for the handful of students who haven't turned it in, because I don't know if sometimes like students might be like waiting around for them to like get turned back. So if they answer keys, right? I'm just going to put it in the gradebook as a 0 if I don't get it by this week, so I can give them back to the rest of you guys. Okay. All right. So let's tackle this Atwood right here. Now, yesterday the starter question involved 2 masses that were pretty close in value. I think it was like 4 and 5 kilograms. Okay. Now they're really different. Ooh, it's like 7 versus 1 kilograms. Okay. So even before you go like plugging and chugging, what do you think the acceleration is going to be closer to, 0 or free fall gravity? Probably a lot closer to what? They're really different values, different masses, right? Like what if you just left an empty string here? That would be free fall gravity for that one, wouldn't it? Okay. Well, if you have a tiny mass, compare that. Well, okay, it's probably not super different. I bet this is going to be closer to 10 meters per second squared than 0 meters per second squared. I'm going to guess maybe like 8, maybe. I forget what the answer is. Right. Right. And then we can, after that, we'll go find the tension. Now the tension, ooh, I bet this is going to be kind of a small tension because this is a kind of a small weight compared to this one. Okay. I bet the tension is going to be probably between 10 and 20 newtons, I'm thinking, somewhere there. Right? Anyway, let's figure this out. Acceleration. Right, so I've been telling you guys 2 main frameworks to solve this. There's 2 main ways you can solve this. You guys take physics in college, right? Math teacher that prefers to do it the other way, right? You could set a free body diagram for each one, right? Set tension versus weight for each one, right? And apply Newton's second law of motion to each individual block. So here's net force equals mass times acceleration for block 1. Here's net force equals mass times acceleration for block 2. If you know the masses in the gravity field, then your 2 unknowns would be, I don't know what is the acceleration, I don't know what is the tension in that connecting string. 2 equations, 2 unknowns, you can solve it that way, right? I think I did it once or twice with you guys that way, right? But the way I normally do it, the way I'll walk you guys through it now, right, is look at it from a systems point of view. And from a systems point of view, there's really only 2 forces that are, like 2 external forces that are driving the system, right? Which are these 2 weights. And tension is internal. So I'm going to start by actually ignoring that, right? And worry about that later, right? So acceleration is going to be the net force, which is the difference in these weights, divided by the total mass. This was the answer to your guys' lab not too long ago, your Atwood lab. So let's do that. Okay. I've got, so acceleration is net, here I'll say the net external force because I'm doing systems point of view on M total. Right. There's Newton's second law of motion, and we're just going to apply it to this. So the acceleration is, right, well, as how many newtons does 7 kilograms weigh? About 70 newtons, right? 70 newtons, right? That's like that force right there, 70 newtons. Right? And this guy over here, guys, if this guy's 1 kilogram, how much does 1 kilogram weigh? Yeah, 10 newtons. Right? So I'm going to subtract those because they're opposite directions. They're competing clockwise versus counterclockwise, right? Now that's acting on 7 kilograms plus 1 kilogram, right? So like forces are vectors. In this case, they're subtracting. So you can add or subtract, in this case, subtract. But masses, inertia, that's a scalar quantity. So I'm just going to add it up. So I have a net force of 60 newtons acting on 8 kilograms. Right? So it's going to drive it with some acceleration. Let's see what is that. I'm looking at 7.5 meters per second squared. Yeah, between 0 acceleration and pure free fall, about 10 meters per second squared. Yeah, this is like 3/4 of the way on the side of pure free fall. Yeah, so it is closer to free fall than 0. Right? That was, I think it was going to be. Right? Right. The follow-up question: what is the tension in the string? Well, I haven't even written anything about the tension of the string so far, right? It's written nowhere on here because it's not an external force. It's an internal force, right? It's internal to the system. Right? So now what I need to do is just isolate one or the other block. I need to just focus on the sky or the sky instead of one or the other equation. And they'll both lead to the exact same answer for the tension force. I think I showed you guys that too. Let's say I pick the small one. Okay. So we can do the tension up minus its weight down is going to result in mass density acceleration. So let's do that. So the net force on the 1 kilogram block equals the mass of the 1 kilogram block times the upward acceleration of that 1 kilogram block. Oh, that's what I meant to mention too. The 7.5 meters per second squared, that's the small block upwards or the large block downwards, right, which is opposite directions. So we got the net force is the tension up minus the weight down. Right? And the tension up, we don't know. That's what we're trying to find out. That's the purpose of what we're doing here. And the weight down was 10 newtons. Right? So the tension up, 10 newtons down. Right? The difference of those is the net force. Okay? The mass of 1 kilogram, of course, is 1 kilogram. And the acceleration, oh, well, we just did all that systems point of view to figure out the value of the acceleration. We got 7.5 meters per second squared. So, yeah. Ooh, 1 times 7.5 is 7.5. Add over 10 newtons. The tension force is 17.5 newtons. There you go. Like a soap. Right. You guys can figure that out. Ooh. I remember some of you guys just knocked off a couple of your quiz questions right there. Okay. Let's see what else we got in chapter 5. Chapter 5. Okay. I think the last one we answered was number 90. We put that in right before the bell yesterday, right? So you're pulling this crate at a constant velocity. They said, what's the coefficient of kinetic friction? Right. Right. So the next question is kind of a similar question, right? They just changed the values that are given and what's unknown, right? So here we got a crate with this given mass pushed with this particular force. Oh, and they told you what is the coefficient of kinetic friction. So calculate the acceleration of the crate. And we do that. So number 91. Okay. I'm gonna make a free body diagram of this crate. So definitely have the full picture of what's going on with this guy. So there's my crate, center of mass. Okay. Let's say I'm like dragging it to the right. Okay. So mass is equal to 225 kilograms. Okay. So that's mass. That I'm pulling horizontally. Here, actually, before I get to that, we draw the. So I bet the weight's like 2,000 and something newtons. Right, that could be. Right. I bet there's a normal force that's exactly balancing that out because it's if it's a level floor and we're not pulling up or down, so nothing crazy there. So it says we're pulling with like 700 something newtons. Right. I'm trying to make these approximately to scale. I'll call this, or you're pushing rather, but same idea, right? F push. Right. And they said there's also a friction, well, they said there's a coefficient of friction, which applies there's going to be a friction force, right? So if you're pushing it to the right, and suppose the block is actually moving to the right, okay, then which way is the friction force? To the left, right? Because the friction's always trying to slow stuff down. Okay. Now they told you coefficient of friction, they say like 0.2. It's 0.2. Is that like 1/5 as a fraction? 1/5 is 0.2. Here, 0.20 is the same thing as 1/5. which means that the friction force needs to be 1/5 of the normal force. Okay. So I'm just thinking about ratios like that as I'm drawing the free body diagram. I'm trying to make these force vectors approximately to scale. Right? Okay, so this needs to be 1/5 of this. Yeah, kind of close. Okay. All right. Write down some numbers here. So they told you that this is 710 newtons pushing force. Right? You could do mass times gravity is that'd be 2250 newtons of weight. Okay? The normal force must be equivalent to the weight because I can say the sum of the forces vertically goes to 0 newtons. Right? No, that's not true horizontally. Horizontally, it's going to be accelerating probably. Okay? But vertically, the block's not moving up or down, so this can be true. Therefore, the normal force minus the weight is 0. Therefore, the normal force is equivalent to the weight. Therefore, that's 2250 newtons. Right? You guys can figure that out? Okay. I mean, if the block's not accelerating up or down, it must be 0 net force vertically. So these two are balanced. That's all I'm saying. Right? Okay. Finally, this friction force, how are we going to get that? Well, that's where we're going to bring in friction force is equal to coefficient of kinetic friction times the normal force. Right? Okay. While you guys are digesting that, I find a poster that's relevant to that. Aha, found it. Okay. So that looks a lot like this poster. No, it's not exactly this poster because this poster I have constant velocity, so everything's in equilibrium, right? But some stuff definitely applies, right? This green box right here, the coefficient of friction, remember, is the ratio of these two forces. A lot of times, a lot of textbooks, you'll see this rearranged as the friction force is equal to these two guys multiplied, coefficient of friction times the normal force. So if you know what your normal force is, and you also know what materials you're working with, therefore you know what the coefficient of friction is, right? Like if it's like glass and glass, I know coefficient of friction. Okay, be like that number, right? Right. Then you can calculate what the normal force is going to be. Okay? Right. So I just took this green equation right here and just rearranged it, and that's what that is. Right? You see that? So we're trying to figure out what is that friction force? What is that? Okay. Well, they said coefficient of friction was 0.2, or you could say 1/5 if you like fractions, 1/5. And the normal force, well, we kind of figured out that had to be equivalent to the weight, so that must be 2250 newtons, right? So you got 0.2 times 2250 newtons, right? 1/5 of 2250 newtons. Let's see, how many newtons is that? And that is 450 newtons. Right? Okay, so we just did a bunch of work there to figure out this must be equivalent to 450 newtons of like drag force, okay? A friction force. Okay. But you notice it has nothing really to do with how hard you're pushing the crate. As long as the crate's in motion, then you know you can use kinetic friction rather than static friction, right? But it doesn't really matter, like the 710 newtons of pushing could have been any number, or for that matter, you could just let the box go and it could slide to a stop. This friction force would still be 450 newtons, right? Okay, because it's going to be 1/5 of the normal force, and normal force equivalent to the weight. All right. So what were they actually asking? Oh, they said what's the acceleration of the crate? Okay. What's the acceleration? Right. So all that setup was like the first half of the problem. Now we're ready for the second half. You guys ready for second half? So take care of free body diagram. Got all the forces are now known. Okay. So the acceleration. What formula are we going to use for acceleration? Newton's second law of motion. Right? Net force on mass. Right? Newton's second law of motion. Right? Right? Oh, what is the net force? Okay. Well, I see vertically everything zeroes out. Actually, I was assuming that to kind of solve that anyway. Right? So I really care about net force. I care about these horizontal forces. There's going to be some net force there, isn't there? Right? Isn't that going to be how hard you're pushing minus the friction? There's going to be some net force between those two. Right? So that's like F push minus the friction force is the net force. Divide that by the mass, you'll get the acceleration. Right? Block's accelerating along the horizontal axis. All right, so we're doing with 710 newtons pushing minus 450 newtons friction resisting that. And the crate was 225 kilograms. So there's the net force, there's the mass. It's all right here. Okay. I'm looking at 1.16, string of fives. That'd be meters per second squared. All right, there we go. So that crate on that surface, you're pushing with that force, it's going to accelerate that much. There could have been an extension question. They could have said, suppose you push that cart for so many seconds. How fast is it going? Or how far is it gone? Right? Or if you know how far it went, could you figure out how fast or how much time it took to get there? Right? They could have had like a kinematic extension, right? Like once you know the acceleration. Okay. Guys, come back. All right, number 97, advertising. What we got here? Joe wishes to hang a sine weighing. Ooh, you both love scientific notation, right? They could have said 750 newtons, but I guess the advantage of writing it this way, 7.50 times 10 to the 2 is now you know that last zero actually is significant. So you know you have 3 significant digits for sure, right? Attached to the store, the cable makes a 30-degree angle with the vertical. Oh, yeah. Yeah, if you have your work and you like staple and like show your work, then yeah, I got some staplers up here. Yeah, that'll be good. Yeah, check it off and give you credit. All right. We got this 30-degree angle from the vertical is this cable. What is the tension in cable B, this horizontal cable right here? If you looked at your take-home quiz, you might notice there's a question that's really similar to that one, right? Okay. So let's figure out what are the tensions in both of the cables. We'll figure out cable A and cable B. How about that? Number 97. What's these tensions here? Set up a Cartesian system right here. Oh, this is not here. So this node right at the center, this is where everything's coming together. We got the sine hanging straight down. That's going to be 750 newtons. So I'll say the weight is 750 newtons straight down. Okay. Got one cable pulling at 30 degrees from the vertical. That's approximately like this. I'll call it, how about T sub A? What's the tension in cable A? Okay. And then there's this cable pulling off to the right. I'll call it T sub B. Okay. This is 30 degrees right there. Okay. You guys okay with that setup? Okay. So 3 forces. We got the weight of the sine, we got the cable up and to the left, we got the cable pulling straight to the right. Okay. Now the principle that you can use to solve this whole thing is, well, I know the sum of the forces has to go to 0 newtons because equilibrium, right? It's just hanging out in equilibrium. That would be true along each axis. Horizontally, that's true. Vertically, that's true. Okay. So we got to have all these forces aligned to the same Cartesian system, right? Oh, and a dash off some axes, and 2 of them are already aligned to that axis system that I put on the board. Right? Only one of them is not. So we're going to take this guy and break it into components. Right? That'd be true. Did I say this cable A is kind of pulling up and kind of pulling to the left? Right? And now we can quantify how much up and how much to the left. Right? Oh, sounds like a job for sine and cosine. Right? I think sine and cosine. So see, this component right here could be whatever the tension is times what? Sine or cosine of 30 degrees? Yeah, like cosine, right? Because we're going from hypotenuse to adjacent. Okay, so this one must be that tension times sine of 30 degrees, because it's opposite of 30 degrees. That be true? Okay. Okay, are we good? Okay. So I'm going to start with the vertical information because we already know a vertical piece of information. Right? We know that this weight is equal to 750 newtons. Isn't that right? Right. Hey, that weight pulling down, is that going to be exactly balanced by the upward component in tension A? Tension A is pulling up and to the left, but it's the only one that's pulling up at all. So I bet the upward component has to be responsible for holding all of the weight. I bet that matches that. Bam, bam. That loses the same thing, right? So let's start with this condition right here. The sum of the forces in y goes to 0. I'm going to say tension A times cosine of 30 degrees minus the weight, which we know is 750 newtons, has to go to 0 newtons. Therefore, just shuffle this around. Tension A cosine 30 degrees is 750 newtons. Therefore, tension A is 750 newtons divided by cosine of 30 degrees. See that? Okay. Cosine 30 degrees, is that some weird fraction? It's like root 3 over 2, I think something like that. Okay. Anyway, I'll just let the calculator handle that. 750 divided by cosine 30 degrees. Okay. I know that tension A is going to be more than. Is that this? Okay. I know that tension A is going to be more than 750 newtons because hypotenuse of the right triangle is going to be along the side. Okay. So let's see what it comes out to. Oh, 866 newtons. Okay. Now that's not what the textbook was asking, but that's an important middle step. 866 newtons. We'll go ahead and box that in anyway. Okay. So now we know this guy is 866 newtons. Is that true? Okay. Now let's switch over and look horizontal. What's going on horizontal? So the sum of the forces in the x direction also goes to 0. Therefore, tension A sine 30 degrees minus tension B goes to 0. Okay. You guys see that tension B is just going to be whatever tension A is times sine of 30 degrees. Right? You see that? Okay. Ooh, who remembers what is sine of 30 degrees? That's a good one to know. What is sine of 30 degrees? 0.5. It is 1/2. Let's go. Hey, so whatever tension A was, it's just half of that. So here, pop this right here. 866 divided by 2. Tension B is 433 newtons. Like that. All right. All right, you guys see that? All right. So vertically, everything zeroes out. We solve for tension A. Horizontally, everything zeroes out. Solve for tension B. Okay. If you like, if you want to be real fancy about it, you could actually program this all so you could go straight from here to here, and there's a tangent type relationship. Because these two legs right here, there's a tangent type relationship. Number 61. I think this is the last one I assigned to you guys. If your textbook is in equilibrium, what can you say about the forces acting on it? Right? Well, anything in equilibrium. What do you know about the sum of the forces? Sum of the forces goes to 0. Here, you got some space right here, it looks like. So 61. I could say that the sum of the forces is 0 newtons. If you want to get even more specific, if you introduce some kind of Cartesian system, you could say in each direction, in the x direction and the y direction. If you want to be real fancy, you could even go to the z direction, right? 0 newtons, right? Other really looking for, I think, is just that first one. Okay. But all right, so equilibrium. We said the sum of the forces goes to 0. You guys know that's what the sigma means, right? Sum of. I told you guys that before. Okay. All right. You guys good there? Let's do some of these next time questions. Aha, here we go. Go ahead and keep in your notes, just keep track of what answer choices you would make, and so you can look back and see like, oh yeah, I'm getting a lot of these right, or at least have some kind of idea. Right, so let's say we're firing this pellet into the spiral tube. Right. When that spiral tube emerges, which direction is it going to follow? A, B, or C? Okay. Show hands. How many guys think it's going to follow path A? Who says path A? Path A. Oh, oops. Who says path B? Who says path B? Path B. Who thinks path C? Okay, so got some votes on each one of those. Okay. Hey, which law of motion do you think is going to apply to this one? Ooh, you guys remember law of inertia? Right. Object at rest, state at rest, but object in motion wants to keep going in a straight line if it can. Right? Like this pellet starts on a curved path, but it's in the curved path because it's forced onto a curved path. Like the wall, like it's always trying to go straight, but it keeps running into a wall, and the wall keeps changing its direction. Right? But that runs out right here. Like right at this moment, now the wall's not pushing on anymore. And at that exact moment, isn't it like moving in that direction? So the answer would be path B. Path B is the correct answer. Yeah. So it just wants to go in a straight line because that normal force from the wall is no longer there. Right? Newton's first law of motion just wants to go in a straight line. Everything in motion just wants to travel in a straight line if it can. And if it's traveling along a curved path, then that's because there's some kind of external force on it. Yeah, there you go. Path B. Law of inertia. Path B. Or two. When the ball at the end of the string swings to the lowest point. Okay, so we have a pendulum set up. About January-ish, we'll look at pendulum motion in this class, right? So we have a ball on a string, we're gonna let go. Oh, what's it? A razor. So let's say that string's gonna hit that razor, right? The string is cut by a sharp razor. Which path will the ball then follow? Okay, so we got A, B, and C. A, B, and C. Same thing. We'll do show of hands. How many guys think option A? Who says option A is going to do? Who says option B? Option B. And who says option C? Option C. Okay. Well, it looks like each one of those gets some votes. Right. So this is also law of inertia. Law of inertia. Okay. So the ball always wants to travel in a straight line. It looks like while it's swinging down, there's a couple of forces on it. Right. It's got the tension and the string, which is always changing, which is kind of weird, right? And then its weight's pulling it down. But it's sort of like geometrically constrained to follow this like circular type path, right? Until this razor cuts the string. Right? At that moment, is the ball in motion? Yeah. In fact, it's moving straight which way? To the right, right? Right. So the answer is going to be option B. The answer is option B, right? Because it's traveling to the right, right? So right at that moment, it's as if you just threw a ball to the right, and then it's going to follow. What shape is that right there? Is that a parabola, right? Because it turns into it turns into a projectile, right? Yeah. Projectile is going to follow a parabola path. Okay, so it's not going to be option A because option A would like make this 90-degree turn, right? Even though gravity's pulling straight down, don't forget it's still moving to the right, right? So it's really like that. And then option C, well, only if the string held it on that curved path, but if the string's cut, they can't do that anymore. So yeah, option B we're looking for. Confirm that. Yeah, the ball continues along path B. There you go, path B. Okay. So there's there we go. Back to your projectile. Ooh, here's a fun one. So we got some ambiguous she holding a book stationary against a wall. Friction on the book acts which way? Up, down, or is that ambiguous too? I can't say. Holding a book against a wall. Which direction does friction act? Maybe I'd want to draw a free body diagram. maybe I'll start with that. Okay. Let's start a free body diagram going on. Let's go against this wall. Okay. It looks like she's probably not pushing straight horizontally. It looks like she's pushing kind of up and to the right. You guys think? Kind of up and to the right? Okay. So here's like the center mass of the book. Okay. I bet this book has at least 3 forces on it, maybe 4 forces, right? Because it's got a weight for sure, right? It's got some kind of mg pulling it down, right? There's some kind of pushing force that looks kind of up and to the right, right? That'd be like F push, right? Oh, is there a normal force from the wall? Or, like pushing out? I'll call it the normal force. Right? Hey, do you guys think that however much she's pushing directly into the wall, because she's not pushing directly into the wall, but there's a component of her push that's going directly into the wall. Do you guys think that that's exactly balanced out by that normal force? Ah, right. So that and their expression of zero net force. Right? Right. Now there's one more force that the book is stationary, possibly, right? Maybe friction, right? Maybe friction. So how should you draw friction? How should you draw friction? So show of hands. How many guys think the friction you should draw upward? Who says upward? Who says downward? Draw the friction downward. Who says it's ambiguous? Ambiguous. Who says that? Because I think it's ambiguous. I think you can't actually say. Okay. Because I could have drawn this free body diagram a little bit differently. Here, let me finish off this one as it is. Okay. So it said in the here's the guiding principle for like equilibrium. Stationary is the type of equilibrium, right? The sum of the forces in the x goes to 0. The sum of the forces in the y direction goes to 0, right? Now, x direction I already took care of in this free body diagram. That is balanced by that. Boom. Okay. But vertically, okay, I had this little bit up, and I gave the book a pretty big weight compared to your pushing force. So in that case, friction would also act upward, wouldn't it? Like friction force. Okay. So that this plus this up balance with this down. Okay. But I didn't have to actually draw like that. I could have drawn this differently. How could this be different? So book, center mass, some pages there. Okay. Okay. What if I had her push really hard on the book? What if F push was like this? Okay. And just to exaggerate the effect, what if the weight of the book is like relatively smaller? Right, something like that. Okay. I bet this is going to play out completely differently. Let's break that pushing force into good horizontal, vertical components. Right. Now the normal force is going to be huge this way. Right. And the friction force, well, look what's going on vertically, because friction always acts parallel to the surface or perpendicular to the normal force, so it has to be like up or down some way. Okay, it's got a wall going on. Okay. But look what's going on vertically. Look at this upper component compared to this downward component. Now I need more force down. The friction force probably does something like this, F sub FR, so that these two forces cancel out with this upper component. Okay. So, imagine that yourself, right? So if you got some object and you're pushing it kind of up and right against the wall, if it's a tiny force, I bet friction is preventing the book from sliding down, so friction acts upward. If you're pushing really hard, then the book is trying to slide up the wall, and so if it's not, then friction is acting downward to prevent that, right? Okay. So it could be either way. Okay, let's see what the answer says. The answer is C. Can't say. Can't say. Oh, and look what they have here. Free body diagrams. A small push. Here's a large push. So I just drew you guys basically these two, right? But it is possible that she could have been pushing with just enough force that friction would have zeroed out, right? So that the weight of the book would have canceled with the upward component of her pushing force. That could have been the case too. There might be zero friction. Right? Ooh, this next one's pretty tricky. Next one's pretty tricky. Look, it's like some kind of modified Atwood, right? So you guys did a lab that looked a lot like this a few days back, right? Modified Atwood type. So we got, saying 100 Newton weight up here, but you guys know what's probably most important about this is 10 kilograms. This could be 10 kilograms here and 10 kilograms here, right? it's acting as a huge mass, like huge inertia to slow down the system. Right? And then we have some kind of weight hanging over the end. Right? Now this one says 100 Newton weight, and this one says 100 Newton pulling force. Right? Now, at a glance, you might think those are identical, but they're actually subtly different. Right? They might actually have a little bit different motions. Okay? In both cases, an applied force, 100 newtons accelerates block. Okay? In which case is the acceleration greater? Like if you're watching these two blocks on the top travel to the right, one of them is actually accelerating faster. Okay. Just think about that one for a few seconds. Okay. Which one's actually accelerating a little bit faster than the other one? Be a subtle difference. Oh, yeah. While you guys are thinking of that, this one's pretty tough. Do a partial free body diagram for each one of these. Free body diagram. Every time it's like sand right. All right. So let's see. Show hands. Show hands. Okay. How many of you guys think the one on the left is accelerating faster? Left is accelerating faster. Who says the one on the right? One on the right is accelerating faster. All right. Well, so how could you use like a diagrams type, right? Okay. So each of these has a 10 kilogram mass up here. Right. So 10 kilogram, 10 kilogram. Right. So each of these top blocks weighs 100 newtons, but there's also 100 Newton normal force that cancels that out and doesn't really drive the motion. Okay. So 100 newtons, 100 newtons, whatever, 100 newtons, 100 newtons, whatever. Okay. Okay. The main purpose of this block up here is that it provides some kind of inertia. Maybe I'm ignoring friction, or maybe you guys have break up a Hot Wheels cars and let it roll, or even if there is friction, it's I don't think gonna really change this answer. Okay. Okay. Well, what about this one that's hanging right here? Start off on the left with a block that weighs 100 newtons. 100 newtons like that, right? Okay. But if this is an accelerating system, right, then the net force on this block cannot be zero. Isn't that true? If it's accelerating, there is a net force. Right? Now, I can think of two forces on this block. Its weight and what other forces also acting on the block? Like a tension force, right? You might do F sub T, like a tension like that. Right? And then you guys think this one string that has one tension in it, and that tension is going to carry over this way? It's going to be like F sub T right here. Right? You guys think? Right? Ooh. But guys, what's bigger, 100 newtons or the tension force? It has to be 100 newtons because there has to be a net force downward on this block so the block can accelerate. Right? See, it's not going constant velocity. It's actually accelerating. Okay? Okay. So when you provide an external force that's 100 newtons, 100 newtons, okay, that's going to manifest as the tension in the string. And this block right here actually will be pulled with the full 100 Newton force, which is a greater force than this block is getting over here, right? So this one on the right is going to accelerate faster. This one has a faster acceleration. Okay. Okay. Check out the answer. Let's make sure. The one block system has a greater acceleration. There you go. There you go. So the one on the right, greater acceleration. Ooh, here's a good one. Right. The brakes are slammed on a speeding truck and it gets to a stop. Okay. Now let's go back and rerun the experiment. And the truck is heavily loaded, so it has twice the total mass. So maybe it started off with like it being 1,000 kilograms. And now we're going to load a bunch of stuff in the back. Now it's like 2,000 kilograms. Okay. Then same thing, same tires, same road, same initial velocity. Okay. And then what is the skidding distance compared to before? Recorder resume. Right, so let's see, show hands, show hands. How many guys think it's the same distance, the same skipping distance? Who says that one? Who says that? Right. Well, that's the answer. That's the answer. Let's take a look. Right. You guys remember this poster right here? This poster right here, which is like right over there on the wall. Right. Right. So this car skids to a stop. Right? This car has a weight and a normal force and a friction force. Right? And if you went back and you loaded up this car's head like twice the mass, then that would give it twice the weight and twice the normal force, but also twice the friction force. Or friction force compared to normal force, that's something to do with coefficient of friction, something to do between the tires and the road, right? So that's a consistent ratio, right? So if you like double the normal force, you'll also double the friction force, right? Let's see this proof here. So here's Newton's second law of motion, right? And the net force would be the friction force because everything vertical cancels, so the friction force is the net force. Friction force is coefficient of friction times normal force. Normal force is the weight. Oh, and right here's where it kicks in. What cancels out on both sides? The mass of the car. So it never mattered how massive the car was. It always slows down. In this case, acceleration could be slowed down, right? It always slows down at the same rate, right? And everything else started the same, like it started with the same speed, blah, 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 right? It would also go the same distance and have the same stopping time. Yeah. Okay. So it's a really classic physics question right there. If you guys take physics in college, like for sure, some version of this is going to come up, right? Where you make the car heavier, what happens to the braking distance? And it's always the same acceleration, therefore it's always the same braking distance. Okay. Right. So the answer should be A, right? Let's just confirm that. 4 times the twice the mass means spinning tires. Okay. All right. Here we go. Twice as much friction, blah, blah, twice as much mass produces the same deceleration, hence the same stopping distance. Yeah, so the same stopping distance, right? This guy down here in this little bubble is actually changing the question. He says twice the speed would change the distance. That would be 4 times the stopping distance. Yeah, okay. So you could do, this little bubble is not what was being asked. This is a different idea. So if you change the initial speed, you could figure this out with kinematic motion. Also, a few weeks from now, we'll do conservation of energy. There's a really good conservation of energy solution to also confirm this would be true. Okay, so if you change the mass of the car, it doesn't change anything. Sorry, doesn't change the acceleration, doesn't change the stopping distance. If you change the initial speed, then that will. Okay. Which encounters a greater force of air resistance, a falling elephant or a falling feather? Ooh, okay. Greater force of air resistance. Show hands. How many guys think there's a greater force on the feather? Greater force on the feather. Who thinks there's a greater air drag on the elephant? On the elephant. Yeah, there you go. It's got to be the elephant. Right? Now, the net effect between the weight of each one and the drag force, that's a different type question. So if you thought it was the feather, you may have been thinking about like net force, right? Because the feather, pretty quickly, the air drag is going to build up to match the weight. So it goes down at constant velocity, right? But the elephant, well, probably not going to happen anytime soon, right? So even though it's a greater drag force, it's also much, much, much greater weight, right? Yeah. So if you drew a free body diagram on H1, the elephant would have a greater drag force, but in proportion to its weight, it wouldn't be not as much. All right. What is the acceleration of the rock thrown straight upward at the moment it reaches the very top of its trajectory? Very top. What's the acceleration? Right. Well, back when we were doing linear and projectile motion, the answer was just free fall gravity, wasn't it? About 10 meters per second squared downward. Okay. Now, if you include air drag, then it gets a bit more complicated. You could say when it's going upwards, it's accelerating down more than 10 meters per second squared. Maybe like 14, 13, 12, 11, 10, right? And then when it's going down, there's the air drag is acting upward and its weight's downward. So it's like partially canceling. So it's accelerating at less than the rate of gravity. So it might be like 9, 8, 7 meters per second squared. Right? But at the very top, where there is no air drag, then you can treat it as if it's in a vacuum because it would be identical. Okay? So the only force is its own weight, and therefore the acceleration would be 10 meters per second squared. Okay. All right. Yeah. So there you go. Right, so it's just G. It's very simply G. Right. All right. That's, ooh, sounds related to this one. As she falls faster and faster through the air, her acceleration. Okay. So her weight stays the same, but that drag force is picking up. Right. And eventually she might reach terminal velocity, right? And guys, terminal velocity, what is her acceleration equal to? 0. Right. So her acceleration must be decreasing. Okay. So she was accelerating at 10 meters per second squared. That eventually works its way towards 0, so that she can go down at constant velocity, which is terminal velocity. All right. There's our pause point today.